Yeah. Good afternoon. Let's begin. Section 6.2, calculating the volume. Of solids. So I'm going to ask you about cylinders and to see whether you know what a cylinder is. So is this a cylinder? Yes or no? Yes. Okay, how about this? Is this a cylinder? Yes. Yes. Perfect. How about this? Yes or no? No? Well, in fact, it is a cylinder if you talk about generalized cylinders. Okay, and so today we're going to talk about generalized cylinders. What is a generalized cylinder? Let's suppose we have a region on a plane, anything at all, like this. Okay. Now I'm going to put a lot of vertical lines through this and replicate the same thing on top. Okay. Okay, so this is a cylinder. So it doesn't look very good, but the top cover should be identical to the bottom cover. Okay, and everything in between are perpendiculars of the same height. Okay, so this is a cylinder whose base is a rectangle. Okay, this is a cylinder whose base is a circle, and so is this. Okay, cylinders are great because we know how to calculate their volume. Okay, and today's lecture is devoted to volumes. So, for instance, this one, if we have the height r, the height h and radius r, then the volume of this is pi r squared times h, right? And the same formula holds here. Okay, it's a very thin cylinder, so pi r squared h. Now for this one, I don't have a general formula like this, but if I know the area of the base, and if I know the height, then the volume of this cylinder is given by the area times height. Okay, so for example here, A, B, H. The volume is given by the area of the base, which is A times B times the height. And obviously that's just the multiplication of the 3 dimensions of this rectangular body. But this is the general formula we're going to use. The reason to use it is that it gives us a way to calculate volumes of anything almost. So let's suppose we have a 3-dimensional space, okay, x, y, and z going out of the blackboard somehow here. I don't want to draw it. And we have a solid situated somewhere between A and B, okay. So something. It's hard to draw in 3D, but just imagine a loaf of bread or something here. Okay. I want to calculate its volume. So this is solid S. Okay. So I'm going to divide the solid into n slabs of equal width delta x. So basically, remember about partitions. I'm going to have a partition here with a step delta x. And I'm going to take a knife and slice this body into slices, vertical slices like this. Okay. So each slice will be like a slice of bread. Okay? So each slice is, in fact, a generalized cylinder. Okay? So the way I do it, I don't take a knife. I take planes, okay, which are perpendicular to the x-axis. So divide the solid in the end slabs of equal width h by planes intersecting the x-axis at points x0 equals a, x1, x2, dot, 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 xn equals b. Okay? Perpendicular planes like this. Planes perpendicular to the x-axis. Okay? And so at each of those slices, I need to determine their area. Okay? So they're going to look like this. What is h? What is the height here? That's delta x, right? Each slice has a height of delta x. Okay? Each slice has the height delta x. And the area is not really constant, okay? But the area can be calculated at a sample point. The areas of the slices is calculated at sample points x, I star. Okay? Therefore, the volume of each slice is V of slice I is the area evaluated at the sample point times the height. Area times the height. A generalized cylinder. And now I can approximate the volume, which is the sum from 1 to n, the area of each slice times its height, volume of slice I, and I take the limit as n goes to infinity to make these slices infinitely thin and to make my approximation better and better and better. Okay. And of course, this limit of the Riemann sum can be denoted by an integral. An integral from a to b, a of x dx. Okay. So a of x is a function of x which tells me the area of each cross-section. And I will give you an example to show how to calculate it. So this is area of cross-sections. Okay. So before I explain this further, I'll just give you an example. And in this first example, again, we will know the answer, such that we can check that we're doing the right thing. So calculate, example, calculate the volume of a sphere of radius r. Okay? So let me place the sphere, place the center of the sphere at the origin. And when I draw it like this, it looks like a circle, right? But it's really a 3D sphere. This is x. Okay. So I can say that this is radius r. Okay. And let's write down the answer before we forget it. So the answer. What is the volume of that sphere? Yes? Do you know that? 4/3 pi r cubed. Okay, we have it down. So whatever we get should coincide with this. So what's the algorithm? We have our sphere. We have to slice it. We are going to slice it in this direction. Okay. So my planes are perpendicular to the x-axis. Let's suppose, so let me remove my attempt to draw 3D. So these smudges were supposed to represent a three-dimensional sphere. You just look at the projection here, right? So if I take a knife and slice it like this, what does the cross-section look like? It's a circle, right? It's a circle that goes like this. Okay. So, so slice it, look at it, it's a circle. So the volume is going to be given by an integral of a of x dx, which these are the areas of my cross sections. What are the limits of integration? This is the extent of my 3D solid. Okay, so x has to go from minus r to r, right? So from minus r to r, all I need to figure out is the area of each circle. So let's practice. You can, first of all, you can see that each slice has a different area. The biggest area corresponds to this slicing. And when I slice here, I just have a little circle, right, that has a small area. And here, so the very last point corresponds to the area of 0. Okay? So I have to figure out the area of those circles. Let's suppose that I'm here. This is my current coordinate x. Calculate a of x. What is the radius at point x? What is the radius of the circle? What is the radius of the cross section? Well, that's given by this, right? This is the radius of my cross section. This is the center of my cross section. It goes like this, and this is the radius. It's given by y. It is y, okay? And we can calculate y from the Pythagorean theorem. What is y? Y squared is r squared minus x squared, correct? So this is y, this is r, this is x. Okay? Therefore, y is square root of r squared minus x squared. R squared minus x squared. For example, when x is 0, what is y? Substitute here, r minus 0 square root. So that's just r. And that's correct. When I slice my sphere in the middle, the radius of the cross section is equal to r. When x is equal to r, when I'm here, I have r squared minus r squared. So my radius of the cross section is 0. Okay, so that gives me a correct formula. So therefore, I can calculate a of x. That's pi y squared. That's the area of a circle of radius y. Okay, area of circle of radius y. So it's pi times this squared, square of square root r squared minus x squared. So this is always the hardest step, to calculate the area of each cross section. Okay? And I've done it. Okay? From now on, it's going to be easy. Let me know if you have questions. So I can substitute this area into my integral. So I have pi r squared minus x squared dx. Okay? And before I go on, I want to apply a theorem that we proved last time. Remember symmetric functions? From 0 to r. It's the same. It's like if I can go from left to right, or I can start from here, do it once, and multiply by a factor of 2. So it's twice from 0 to r pi r squared minus x squared. The rest is really easy. So 2 pi, and I have to take the antiderivative of what? R squared minus x squared. And remember, r is just a constant. So this is a very easy integral to take. I have r squared is a constant times x minus x cubed over 3 integrated from 0 to r. 2 pi. When I substitute here, I get r cubed, and this is r cubed over 3. And when I substitute 0, I get 0. That's why it's nice to replace it by twice the integral from 0 to r. So what's the answer? 2 pi times 2/3 r cubed Does this look right? Okay. So we did get the same answer. Okay. Questions? Okay, so we only have to do the sphere once. The rest of the problems, we don't know the answer. Okay. So let's try some of those. So here's a typical problem. Calculate the volume of the solid obtained by rotating the curve y equals x cubed for between 0 and 1 around the x-axis. Okay, so we don't say a sphere or any known thing like this. This is something that we have to imagine what it is. We have to figure out what the solid is. Okay, so to do that, we start by drawing that curve they're talking about. Very easy curve. So y equals x cubed. And I'm only interested in the interval between 0 and 1. It looks like this. Now what does it do? We take this curve and rotate it. Okay, rotating. We rotate this. Think of it as a piece of wire, okay? And we rotate it around the x-axis in this direction. What do you see? It's kind of like a cone,
Martini cup.
or martini cup, or a Hershey's Kiss. Okay, this shape, Hershey's Kiss. Martini cup, yes. Like this. And so this is a 2D projection of it. Of course, it's circular. It's a cone. It's kind of a cone. Okay, so I'll draw it once for. So it looks like this, right? I'm going to erase my three-dimensional drawing because we will need this plot to figure out the things for my integral. Okay, So this is x, y. So what do? We have to, for each point x, we have to figure out the area of the intersection. I'm going to slice this martini cup at each x. What is the shape of the intersection? Circle, right? Because it's obtained by rotation of this thing. The intersections are circles. So intersections are circles. What is the radius? What is the radius of this circle when it intersects here? So this is x. Y is x cubed. So the radius is just given by the function at this point, right? The radius is x cubed. The area is a of x equals pi x cubed squared, because it's a circle. Okay? So it's pi x to the 6. And I'm done with the hardest part. Okay, so this is the part which you need to understand. So let me just tell you that with problems like this, when we obtain a circle by rotating something, it's called, the resulting object is called a solid of revolution. A solid of revolution. Okay, when something is revolving around something else. Now, solids of revolution are great because the intersections are circles by construction. Intersections are circles. Makes it totally easy to calculate their area. If we know the radius, and we do know the radius here because we know the function, we know the radius and we know the area. Now we can just go through the motions. The volume is given by an integrating of a of x dx. From where to where? Well, that's given, right? From 0 to 1. So go from 0 to 1 of this thing. Pi x to the 6th. Pi over 7 is the answer. Question?
I was wondering about the radius, how when you're going through each slice, the radius is changing, right?
Absolutely.
But we can assume that it's a constant.
No, it changes. So when I slice it here, the radius is x cubed. Okay, so when I slice near 0, it's very, very small. When I slice near 1, it's 1 cubed, which is 1. So in this integral, it's changing with x. It's not a constant.
Oh, okay. I thought you said, like, when you're integrating it, like, I thought you said it was a constant. That's why. The radius.
The radius, no, so for here, here the radius for each intersection is x cubed. And area is pi x to the 6th. So for each x, the radius changes. It wouldn't change if I had a solid of this kind. Let's suppose my solid is given by y equals 1. Okay? So it's this function from 0 to 1. When I rotate this around the x-axis, what do I get? A real cylinder, right? A real cylinder. So in this case, my radius is equal to 1, and area is equal to pi 1 squared. So the volume of this would be from 0 to 1, pi times 1 dx. So that's pi. So in this particular case, you can see that the radius is the same for each slice, but not here. Okay? Most of the time, it's not a constant. Now let's rotate the same thing around the y-axis and see what we get. So rotate the same curve around the y-axis. And I have to draw again now, okay? So here y is x cubed, okay? And now I have to rotate it in this direction. So this is 1. This is 1. What does it look like? It does not look like a Hershey's Kiss anymore, right? It's a different shape. It's a ball. Yes. And now it's a solid of revolution obtained by rotating around the y-axis. So if I slice it in this direction, my intersections are going to be things like this, and I really don't know how to calculate their area. Okay? But if I slice it in this direction, what are my intersections? Circles, because it's a ball in this direction. So it's to my advantage to integrate over the y-axis. Okay? So we can slice in the direction perpendicular to the y-axis. So the volume will be given by the same formula, only in terms of y. And we need to figure out the radius and the area of each intersection for each point y. So what are the limits of integration? X goes from 0 to 1. How about y? Because y equals x cubed. When x equals 0, y is 0. When x equals 1, y is also 1. So by coincidence, we have the same limits of integration. They didn't have to be. If this was 2x cubed, then my limit of integration would be from 0 to 2, right? So fine. So now we have to figure out for a given point y, what's the radius of the intersection here. Okay? So this is given by x, right? So given y, this is y. The radius is given by x. I have to figure out x given y. So if y is x cubed, then x is y 1/3, right? So this is the radius. And area is pi times this squared. So pi y 2/3. Questions? So my operation here is slightly different. I have to express everything in terms of y. Given y, I'm going to change my y from 0 to 1. Given y, what's this length? This length is given by x. Y and x are related like this, so I have to solve for x in terms of y. So I reverse my function. And you always do this when you integrate in the y direction. Okay? You kind of have to resolve everything in terms of y. So now the hardest part is over. And I just write down the formula pi y 2/3. Okay? So pi y 5/3 from 0 to 1. 3 pi over 5. So which one is bigger? When I rotate around the x-axis or when I rotate around the y-axis? This one is bigger. You can see 3 pi over 5 is greater than pi over 7 because this one is skinny and this one is fat, right? You can tell. Okay. Fine. All these problems, they get increasingly worse. So the next step is the following. Calculate the volume of the solid obtained by rotating region R around the x-axis. What is region R? Region R is given, is enclosed by curves y equals x to the fourth, y equals 8x, and x between 0 and 4. Okay. So when they start talking about region R, this is what we draw first. Okay. So one curve is a straight line, 8x, like this. And the other one is a parabola. And this is region R. So this is y equals 8x. This is y equals x to the fourth. Okay. Let's find the intersection. Okay. Find the intersections. We learned it last time. We have to equate them, right? X to the fourth is equal to 8x. So I have x cubed minus 8 equals 0. What are the answers? X equals 0 and x equals 2, right? So this point here is 2. I don't see the point of this condition, actually. Let's erase it. OK. Now, how do we visualize the solid? We have to take this piece, like this wing type thing, and we rotate it around the x-axis. So this is the x-axis. We're going to spin it like this. What do we see? So if we look from the outside, we actually see a straight cone, right? The outer surface is straight. Now, it's not just a cone, because I can put my hand here, and there's nothing there. So it's a kind of a hollow cone, right? It has a certain width to its walls, but it's hollow inside. So what happens if I make a cross-section in this direction? What is the shape of that cross-section? Is this a circle? No, it's something else. What does it look like? Draw it in your notes. Figure it out. Does it look like this? When it... What do you call this? A disc? A disc was just like this, right? But it's not. It's hollow inside. A washer. Or a donut. OK, this is a washer. When I started teaching this class, I didn't know what a washer was, except for a dishwasher. This is not it. It's a thing that looks like this, OK? You can call it a donut, but it's flat. OK? So this is a cross-section when I slice this cone in this direction because of this structure. And it's totally easy to calculate the area of this object because it's the outer circle minus the inner circle, right? So if I know the outer radius and I know the inner radius, I can calculate the area of this cross-section. So let's do that. So what is the area of a washer of radii? So a washer is characterized by two radii, right? An inner and one and an outer one. So let's draw it like this. This is y out, and this is y in. bad, sorry. So the area is given by, of course, pi y out squared minus pi y in squared. I take the whole area and I take out the area of the hole in the middle, right? Hole of the donut gets subtracted, okay? So what I'm after here is the areas of the cross sections, and I have to figure out the inner and the outer radii of the washers, given that solid. Perhaps I'll go back to here. And mark it here. So let's suppose I'm making my cross section here. This is x. So I have to go from the center. What is the radius of the outer circle? Y out. That's given by the outer function, the one that's furthest away from the axis. Which one is it? 8x, the straight line. Okay? And y in is therefore x to the fourth. Okay, so this is x to the fourth, and this is 8x. Now I go back, and I can calculate a of x is pi, and I have 8x squared minus pi x to the fourth squared. At this point, I can simplify a little bit, and then I'm almost done. So I have 16x squared minus x to, oh, yes, 64. Thank you. Like this. And I'm done with the hard part. So now the volume of the whole solid of revolution is an integral from 0 to 2, y2, because my solid runs from 0 to 2. We calculated the point of intersection. A of x dx. So from 0 to 2, pi can go outside. 64x squared minus x to the 8th. And the rest is easy. Can I just give you the answer here, or do you want me to go through the steps? Skip the steps. Okay, so all I need to do times pi. All I need to do is calculate the antiderivative of these simple powers. Okay. Okay, it gets worse. Okay. Now I'm going to take the same region and rotate it around something else. Rotate the same region R around the axis y equals 20. So that's going to be quite different. So let me leave this picture. And figure out what this is. My region R is the same x. So let's find out what this point is. In terms of x, we have x equals 2. What is y here? So because this is both lines x to the fourth or 8x, this is 16. And my axis corresponds to y equals 20. So it's here. I have to draw this axis. Then take this petal or this wing and start rotating it around this axis, like this. Okay? So what do we see? What is it? This is a ball without a bottom. Can you see this? So let me draw it here. Just kind of. It's something that looks like this. So the projection looks like this. So if you put a disk here, that would be a ball. I could eat from here, right? But it doesn't have a bottom. Do you see this? Is it clear what we have here? OK. So what are the cross sections in this direction? Washers again. OK. I want to draw it better. So imagine a ball like this. Now the walls are a little bit thick like this. And the bottom is missing. Okay, so if I slice it like this, I'm going to get a washer. So cross sections are washers. The hard bit here is to figure out the radii. Okay? So let us try to do this. So the radius is the distance between the center and the edge, right? So we are going to measure our distances from the center, not from here. We are not rotating around the x-axis. We are rotating around this axis. So what is the inner radius corresponding to x? So it's the distance between this and this. I can denote it y inner. Okay? So y inner. How do I obtain this distance? What is this distance? This is 8x. Right? So corresponding to x, the top function is 8x. So this is 20 minus 8x. Okay? And the outer radius is given by the distance from the center all the way down to this function. So it's 20 minus x to the fourth. X to the fourth. Okay? So now the area of the cross section is pi I out squared minus pi y in squared. Okay? So pi, and I go 20 minus 8x squared minus 20 minus x to the fourth squared. And now I have to.
Your 8x is your inside radius.
I know I'm wrong because everybody says it, but I don't. Is this correct?
Yes.
Yeah.
It should be 20 minus x to the fourth.
Oh.
Minus square minus the.
So 8x is the inside and.
Oh, x, y out. Oh, yes, yes, yes. Thank you so much. Thank you. X to the fourth. Yeah, so see, if you get them confused, then you get a negative volume. Would be not so, like this, right? Thank you. Now, tedious part begins, because, so before I use this in my integral, I have to simplify it. This is the stage at which I simplify. Okay? So I have, look at this. 400 goes. And that's all the simplification I get. So let's go here. So the volume is an integral from 0 to 2 a of x dx. So it's pi 0 to 2 of this whole thing. And this is totally easy but tedious, so I skipped one step to give you the answer. Okay? And you can check it because I know this is correct. I did it at home. Okay? So, question?
How did you get to divide by 9?
Am I mad at you? Why? This is gross?
Ridiculous.
You don't like it? Well, it gets worse.
For the exams, are we expected to simplify it to the final stage, or can we just like plug it in?
So, for my midterms, I'll try. So, these are problems that you can expect for the final and midterms. Okay? Maybe not so bad for this midterm, but for the final for sure. And we try to give you algebra that is better than this. Okay? Such that you can do it without a calculator. Okay? So let me just talk to you a little bit about the plan. Okay? So I'm going to have a whole, almost the whole lecture on Wednesday devoted to the midterm. The midterm is on Friday. Okay? And we still have one very small section to cover because we have one fewer lectures than sections that we need to cover. So in the last 5 minutes, I'm going to explain to you one of the simplest things. Okay, compared to this, it's very easy. And then I'll let you go, and on Wednesday we do review. Okay, so the section that I need to cover now is section 6.5. Average value of a function. Okay, so if I were to calculate the average height of students in this room, the rule is simple. I take everybody's height, I add them up, and I divide by the number of students. So this is clear. Now, if I want to calculate the average temperature, it's harder, okay, because temperature as a function of time is a continuous function. What am I going to add up and divide by how many, right? So an average value of a function can be calculated approximately by pretending that I have a number of discrete values. So what I do is I'm going to split this function into a number of points, okay? x0, x1, x2, and so on, okay? I'm going to add these and divide by n, as many as I have values. So let me give you an example. Temperature, so time in hours, and temperature in Fahrenheit. So let's suppose I take this graph, and I use values 1, 2. We're going to only do 6 hours, okay? So let's suppose that the temperature was 70, 72, 80, 72, 75, 76, and 60. Okay? So I split the 6 hours into 1 hour period, recorded the temperature at the top of each hour, and now I can calculate the average temperature. Obviously, it's given by the sum of all the measurements. Divided by, actually I have 7 because I also counted 0. So it's 72.86. Now, of course, I could have measured the temperature every second, and that would make this calculation of average more precise. And in fact, I can take the limit. So for a continuous function, we are going to say that f average is going to be equal to f of x1 plus f of x2 and so on, f of xn divided by n. Okay? These are sampling points. I have a partition. I measured the temperature for each of the intervals. I add them up and I divide by how many I have. Okay? So this is approximate. Okay? And I can take the limit to make it exact. So it almost looks like our integrals, but not quite. What's the difference? We divide by n and we don't multiply by delta x. But this is very easily fixed. So let's recall that delta x is nothing but b minus a over n. Okay? Therefore, 1 over n is the same as delta x over b minus a. So I'm going to rewrite this like this. The limit as n goes to infinity of the same thing. And instead of 1 over n, I put delta x divided by b minus a. So now I have everything that is in the integral, and I divide it by b minus a. So by definition, I rewrite it as an integral from a to b, f of x dx divided by the length of the interval. Question?
Where did you get 77 from?
77? Oh, I don't know. 80, 72, right? I'm sorry. I was hoping somebody would ask. Okay. So, to summarize, how do we calculate the average value of a function on an interval between a and b? We take the integral f of x dx and we divide it by the length of the interval. One example, and I'll let you go. So find average value of the function sine x for the interval between 0 and 2 pi. Let's do this. So f average. By definition, I have to integrate from 0 to 2 pi sine x dx, and I have to divide by 2 pi minus 0, right? So that's all we do. We just have to evaluate the integral over the whole interval, and interval is always specified, and divide by the length. What's the answer here? So I get minus cosine x of 0 and 2 pi. I have minus 1 minus negative 1. Okay? Is 0. Let me illustrate on. I have to give you this example. Let's draw a sine. Okay. What's the average value of this function between 0 and 2 pi? Think of it as snow or sand. For Californian people, it's sand. For Russians, it's snow. Okay. I want to make the average level. So I take a shovel, and I take it from here and fill it up, fill it here. And so when I make the actual average level, it is 0. Okay? And that is the procedure that is explained by this integral. Thank you very much.